So today it's my really great pleasure, for the first lecture of the year. I think it's hard to find somebody better than Jeff Barrett. So to introduce Jeff to give the first lecture of this series this year. And it's, as most of you know, Jeff works on the philosophy of physics, more precisely on quantum mechanics, and also on other topics related to game theory and to the evolution of language, evolution of communication, evolution of scientific practices. I understand that's what you've been doing extensively in recent years.
Both are great.
Both are great. Okay, wonderful. Jeff, as you know, is professor at Irvine in the LPS department and also in the philosophy department. And it's a wonderful choice for today's lecture because he's a former visiting fellow at the center. He was here in 96, 97. So it's always good to have him back. And he's been the editor of Philosophy of Science for now many years. So many of you owe him thanks because he's accepted your papers.
We can talk about that later.
So you want to talk to him after because he's rejected your papers.
Almost never happens.
But you'll deal with that issue after the lecture. So Jeff, thank you very much. It's going to be looking about typical words.
Thank you very much. There are few places I feel as much at home as here. This is a cluster of topics that I've been thinking about for the last several months, and so here's the upshot of it. It follows on thoughts on no-collapse formulations of quantum mechanics. It's tempting, and we know this temptation as philosophers. It's tempting to claim that one can derive strong conclusions from weak assumptions, but there's a no magic constraint. The conclusion of a valid deductive argument can't be stronger than the premises that we use to get it. And it's easy to say that. If we get a strong conclusion, we must have made similarly strong assumptions somewhere along the way. It's easy to say that. What's not so easy is saying where those extra assumptions snuck in. And that's what the puzzle is for us today. Both physicists and philosophers of physics have repeatedly claimed to be able to deduce the standard quantum probabilities from Hugh Everett III's pure wave mechanics. Now, what would make this magic is that pure wave mechanics is a deterministic theory that says nothing whatsoever about probabilities. So if you could deduce claims about probabilities from the theory, that would be impressive indeed. Everett presented pure wave mechanics, the many worlds interpretation, as it's sometimes known, as a solution to the quantum measurement problem. While pure wave mechanics says nothing about probability, Everett thought that he could do something in the direction of getting probabilities from it. What I'm going to suggest is that he really wasn't driving probabilities in the standard sense, but he had a more modest task at hand. He thought there was a sense it could be understood as making the same statistical predictions as the standard von Neumann Dirac formulation of quantum mechanics, the collapse theory. His goal specifically was to show that the relative measurement records of a typical relative observer will exhibit the standard quantum statistics. And much of the talk is going to be dedicated to unpacking what that little blue phrase means there. Everett used the von Neumann Dirac formulation of quantum mechanics, the standard formulation, to explain how he understood the quantum measurement problem and to characterize his new theory, pure wave mechanics. So it served this dual purpose. Following von Neumann, Everett took the standard formulation of quantum mechanics to be the following principles. And I'll illustrate these with pens. I just decided this as I looked around the room, and I thought, hey, this might work. So that's as strong as I can go. So the standard formulation of quantum mechanics, the standard collapse formulation of quantum mechanics, has a handful of principles. The first is that the state of any physical system, a chair, an electron, the planet Earth, can be represented by a unit-length vector in a vector space. You can think of that as this pen. It has a magnitude and a direction, and the magnitude is 1. An observable can be represented by an orthogonal set of unit-length vectors. Here's an observable. This observable might represent the chair being in the room, the blue pen vector, the chair being out of the room, the red vector. Now these are orthogonal to each other and they form an orthonormal basis. The actual state of the chair might be in the room or out of the room or at a 45-degree angle to being in the room and out of the room. That doesn't mean it's kind of in the room, or kind of in the doorway. It means it's in a superposition of being in the room and out of the room. And there's a standard interpretation of states. A physical system S has a determinate value for observable O if and only if the state of the system is one of those special eigenstates. So the chair is determinately in the room if and only if that's the state, and it's determinately out of the room if and only if that's the state. And if it's not either of those two states, it's not determinately in the room or determinately out of the room. It's in a superposition. And there are two dynamical laws in the theory. The first is, if there's no measurement made on the system, then it evolves in a linear, unitary, deterministic way. So if this is the state at time t0, we apply a unitary operator to that state, and we get the state at time t1. And that unitary operator just depends on the energy properties of the system. Fully deterministic. The second dynamical law is the nonlinear collapse dynamics. If I observe the chair, suppose it starts off not in the room and not out of the room. If I observe it, its state will instantaneously jump to one of the states where it's either in the room or out of the room. And the probabilities are determined by taking the projection of this vector onto this one and squaring the length of that projection. And so it's this rule, the nonlinear collapse dynamics, that gives us probabilities in the standard formulation of quantum mechanics. If we didn't have this rule, we'd have a theory that has no probabilities at all, no talk of probabilities, no probabilistic predictions, just a unitary deterministic dynamics. Now, the theory that Everett thought was the right formulation of quantum mechanics is this theory, but without this second law. That theory without the second law is called pure wave mechanics. This is what Everett called it. And so the game is, can we get probabilistic predictions from just pure wave mechanics without adding anything to it? The answer is no, because it doesn't say anything about probabilities. But we need to proceed carefully here. The next question would be, well, what would we have to add to it in order to get probabilistic predictions? What's the minimum that we would have to add? Do we have to add something that's crazy and strong that uses primitive as a measurement as an undefined primitive term? Okay. So Everett held that the standard von Neumann collapse theory, the one that I just had up there, was inconsistent and hence untenable. He examined the question of the consistency of the standard theory by considering something he called an amusing but extremely hypothetical drama. Now, Everett wrote about this stuff when he was a graduate student at Princeton in the philosophy department, and in the physics department, and his advisor was John Wheeler. For many years, we really didn't know much about the process that generated his PhD thesis. We had the thesis, but we didn't have his notes and such. Recently, though, we have all the notes that he wrote as a graduate student and the revisions of his thesis, and so we know much more about the trajectory that he followed here. This is a little known bit of the story. People should have known more about this, but they didn't. Everett's worry about the standard collapse formulation of quantum mechanics was communicated in his thesis, the long version of his thesis, by his telling of something that's come to be called the Wigner's friend story. Now, Everett told this story before Wigner did. Wigner was at Princeton as well. He was on the faculty. There's good reason to suppose, given the new historical evidence that we have, that Wigner actually copied this story from Everett and then used it later on, and it became the Wigner's friend story when there's good reason to suppose it was Everett's story to begin with and was being circulated in that context. And it goes like this. We have our friend inside a box, a measuring device and a system S. And we have an external observer. And so it's a nested measurement. The friend is going to be making a measurement of system S. the external observer is going to be making a measurement of this whole system composed of the friend, the measuring device, and the system. Now, the system starts off in a superposition, and it's kind of hard to read this given the way the screen's working, but I'll read it out loud. A superposition of alpha times x spin up plus beta times x spin down, and system S might be a spin 1/2 particle, for example. So it's not x spin up, it's not x spin down, it's not both, it's not neither, it's a superposition. The measuring device starts off ready, the friend starts off ready to look at the measuring device. Now, this is a good measuring device and a good friend observer, and what that means for Everett is when the measuring device interacts with the system, if the system were x spin up, I'll use this fancy pointer, if it were x spin up, the pointer on the measuring device would just swing over to x spin up and say, the result's x spin up. If it were x spin down, the pointer on the measuring device would just spin over, or move over to x spin down and report that it's x spin down. Similarly, when the friend looks at the pointer on the measuring device's brain state, will go from I'm ready to look at the pointer to I see the pointer pointing it up or I see the pointer pointing it down. Now that's if S were x spin up or x spin down. But that entails something. If we assume these perfect correlating interactions as Everett does, then the linear dynamics, that's rule 4.1, that first dynamical law, predicts that the resultant state inside the box will be this superposition. The friend's not going to get up or down as the result. Rather, we'll have a superposition of the friend getting the result up, the measuring device being pointing it at up, the system being x spin up, superposed with the friend getting the result x spin down because the measuring device is pointing at the result x spin down because the system is x spin down. But this doesn't happen. That doesn't happen. It's a superposition of the two things that happens on the linear dynamics. So we know what the linear dynamics predicts here. Now what Everett said about this is an observer outside the box, and I've labeled this W for Wigner because this is to make a Wigner's friend. This observer outside the box will calculate the state inside the box by the linear dynamics to be that. And this observer outside the box might have a special measuring device called, let's call it an A measuring device. It measures an observable of this composite system. And we could take this state, Everett suggests, to be a result +1 for this A measurement. And we could take a state like this but with a minus sign, something orthogonal to this state, to be result for A measurement of -1. So if this is the state, if Wigner on the outside makes a measurement of the observable that has this as an eigenstate corresponding to the result +1, he's going to be guaranteed to get +1 as the result. And it will indicate to the guy on the outside that that's what the state of the contents of the box is. Okay, so that's on the unitary dynamics. But on the standard collapse formulation of quantum mechanics, and this is what Everett's trying to cause problems for, if we suppose there's something special about the friend that causes a collapse of the state, and we take the friend's perspective, and it collapses the object system on measurement, then the state predicted by the collapse dynamics is either this one or this one, the friend getting up or the friend getting down. And the probability of this happening is alpha squared, and the probability of this one happening is beta squared. We just take those coefficients and square them. That gives us the probabilities of each of those outcomes occurring. So here's the first point. The linear dynamics predicts a completely different state than what the collapse dynamics does. If we don't know if there's been a collapse of the quantum mechanical state, then we're not going to know whether this obtains or these obtain. And we don't know if there's been a collapse of the quantum mechanical state unless we know whether one of the interactions inside the box should count as a measurement or not. But the theory doesn't tell us what should count as a measurement. The upshot is the two dynamical laws they predict incompatible states when applied to the same interaction. Now, Everett's conclusion was the theory is inconsistent. A more charitable conclusion would be, well, it's incomplete. We just need to know what interactions count as measurements in order to know when collapses occur. But this is something else that Everett noticed, and that is that these states are in principle distinguishable from this state. And they're distinguishable by something like an A measurement from the outside. And so this nested measurement setup, where there's a measurement inside and then a measurement of the measurer, was something that caused problems with the standard formulation of quantum mechanics. And that was what Everett was worried about. And this is what he called his hypothetical, amusing story, which of course has been retold as Wigner's friend's story. So Everett held that one only has a satisfactory formulation of quantum mechanics if one's theory can consistently describe such nested measurements. If you can't handle nested measurements like that, you don't have a good theory. And it was clear, Everett was clear about how the Wigner story should go. So how did he think that little episode should be described? He believed that the external observer's state was correct. Inside the box, the real state is the friend's in an entangled superposition of getting x spin up and x spin down. He's committed to that. And he has to be committed to that because he's going to throw away the collapse dynamics. Further, he believed that an external observer would be able to show this by an appropriate interference experiment. Somebody sitting outside would, in principle, be able to measure this A observable and show that that was the state, that entangled superposition. But he also believed that from the perspective of the friend inside the box, it would seem as if the friend had gotten a perfectly ordinary result to his measurement, her measurement. And he believed that he could recover the standard quantum statistics for those appearances to the friend inside the box. So the problem is, how do we satisfy those four conditions together? These two are easy, but if we satisfy these two conditions, then how do we explain how the friend got a definite result inside the box? And then how do we get the standard quantum statistics? So Everett took pure wave mechanics to be the standard von Neumann-Dirac formulation, but without the collapse dynamics, without that 4-2 rule. And he thought that that explained how these four constraints could be met and hence provided a satisfactory resolution to the quantum measurement problem. So let's go through what he actually says. He describes his project this way, quote, "We shall deduce the probabilistic assertions of the collapse dynamics, rule 4-2, as subjective appearances to the friend inside the box. To observers who are themselves treated as perfectly ordinary physical systems always subject to the linear dynamics." Quote, "Thus placing the theory in correspondence with experience. We are then led to the novel situation in which the formal theory is objectively continuous and causal, while subjectively discontinuous and probabilistic." He took this to solve the nested measurement problem because, quote, "While this point of view shall ultimately justify our use of the statistical assertions of the orthodox view, it enables us to do so in a logically consistent manner, allowing for the existence of other observers." Okay, so how did this work? Right, we've seen what his statement of his project was. How did he get it? Well, the first thing he does is he introduces a distinction between absolute records and relative records. While pure wave mechanics does not describe an observer as having any particular absolute record after a typical measurement interaction, it does describe the observer as having a number of different relative records. In the case of the Wigner's friend story, Everett thought this was the state at the end of the interaction of the friend with the measuring device in the friend's system. There's no absolute measurement record here, right? It's not up, it's not down. Everett believed the eigenvalue-eigenstate link with respect to absolute records. But there are relative records here. Relative to the system being x spin up, the friend got x spin up. Relative to the system being x spin down, the friend got x spin down. So there aren't absolute records, but there are relative records. And those records are relative to the branch. We have one branch here, we have another branch here. In this branch, the friend got up. In this branch, the friend got down. In this branch, the friend got up and the system is in the x spin up state. In this branch, the friend got down and the system is in the x spin down state. Everett took the existence of branches where an observer has determinate relative records to explain the observer's determinate experience. As he put it to Abner Shimoni some years later, this was just in discussion, it was recorded because it was at a conference. Everett said, each individual branch looks like a perfectly respectable world where definite things have happened. Now, Everett didn't talk about his theory as the many worlds interpretation of quantum mechanics in print. But when he was talking to people just across the room, he'd say things like this. This is like a world, this branch, a world where the friend gets up. This is like a perfectly respectable world, a world where the friend gets up, spin down as the result of his measurement. Now, if those really are worlds, that would explain why the friend gets a definite result. Because there are two friends. One friend gets up and the other friend gets down. They both get perfectly determinate results. The sense in which Everett thought that each branch would look like a perfectly respectable world, however, takes some care to sort out. We're not going to do that here. I think it can be sorted, but it requires some subtlety. For our present purposes, we'll just suppose that we can sort this out. And we'll turn to consider Everett's account of statistics, quantum statistics. Okay. So we're setting aside the determinate record problem for Everett, and we're considering the probability problem for Everett. Everett clearly and repeatedly insisted that there were no probabilities in pure wave mechanics. Indeed, he originally entitled his PhD thesis, Wave Mechanics Without Probability. There aren't probabilities here. Rather than claim that his theory predicted the same chance events as predicted by the standard collapse dynamics, Everett argued that it would appear to a typical relative observer that there had been such events. Specifically, he argued that an observer's relative measurement records in a typical branch would appear to be randomly distributed with the standard quantum probabilities. So his argument is going to depend upon a notion of typicality that he introduces that extends across these worlds, that extends across these branches. He wants it to turn out to be the case that a typical world, a typical branch, will exhibit the standard quantum statistics. Everett took the problem of finding an appropriate notion of typicality here to be analogous to the problem of finding an appropriate typicality measure in statistical mechanics. His strategy was to impose a sequence of desirable constraints until a particular typicality measure was uniquely determined. Specifically, he did not argue that almost all branches by count will exhibit the standard quantum statistics. The reason he didn't argue this is it's false. If we look at the branches that we have, and we look at those that exhibit the standard quantum statistics, typically, most branches will not. So if he wants to argue that a typical branch will, he can't just have a notion of typicality that depends upon the count of the branches. Rather, he argued that almost all branches in a specified measure M, which he took to be particularly natural, given the mathematical structure of the theory, will exhibit the standard quantum statistics. Okay. While Everett was careful to explain that this typicality measure M did not represent probabilities, it did satisfy the formal conditions for being a probability measure over branches. Namely, M's a set function that assigns a number between 0 and 1 to each subset of branches in a chosen decomposition of the state, such that the total measure assigned to the branches is 1. If Q gets assigned a measure, then it's 1 minus the measure assigned to the complement. If R and Q are mutually exclusive, then if they're disjoint, then the measure that you assign to the union is the sum of the measures. And then you assume that the measure is countably additive over disjoint subsets of branches. Over and above this, Everett had 3 constraints that he places on his measure. And he wants these to pick out a single measure in the theory. Everett's first constraint was that M be a positive function of the complex valued coefficients associated with the branches in the superposition. So a typical superposition is a sum of a bunch of branch states, each with a coefficient AI. He wanted the measure over these branches to just be a function of those coefficients. That seems reasonable enough. In fact, there's not much else you could use here as your basis for a measure in the theory, short of just counting up the branches, which is a natural thing to do, but this is another natural thing to do. His second constraint was that m be a function of the So his second constraint was that this be a function of the amplitudes of the coefficients alone, rather than the full information contained in the amplitudes. And the reason he gave is that the coefficients on the branches can only be empirically determined up to an arbitrary phase factor. Finally, this is his third condition, he stipulated a sub-branch additivity condition that he wanted to have satisfied. Any collection of branches, bi, in the total state could be considered to be a single branch on a different orthogonal decomposition of the state. Everett stipulated that the measure associated to that single branch be equal to the sum of the measures associated to the branches that constitute that single branch on a different decomposition of the state. This is a natural enough thing to do. One of the things it does is it ensures conservation of typicality under the linear dynamics. So if I have a branch on the linear dynamics and it's typical, it has typicality T, and I run the linear dynamics and it splits into a bunch of branches. Then if I sum up the typicalities on those sub-branches, then I'll get the typicality of the original branch that's split into those. Okay, those are his constraints. And together, Everett took these three constraints to determine uniquely the typicality measure as the norm squared amplitude measure on branches. So let's go back to our state at the end of the Wigner's friend experiment. There are two branches. They're both here. One branch has a coefficient alpha on, the other branch has a coefficient beta on it. The measure that Everett wants on this branch is alpha squared, norm of alpha squared. The measure he wants on this branch is the norm of beta squared. That's going to be his typicality measure. It's not that the probability of this branch is alpha squared. It's just that's the typicality measure assigned to it. The probability of this branch is 1. The probability of this branch is 1. They both happen. Because m does not represent probabilities. Indeed, inasmuch as Everett took all the branches to be equally actual, he took the probability of each branch to be 1, and he explicitly does so. And let's look at this. Everett believed that all the branches were equally actual because he believed that it was always in principle possible to observe interference effects between them. This is something that many Everettians miss. Let's look at Everett in this regard. We take this opportunity to caution against a certain viewpoint which can lead to difficulties. This is the idea that after an apparatus has interacted with a system, in actuality, one or the other of the elements of the resulting superposition described by the composite state function has been realized to the exclusion of the rest, the existing one simply being unknown to the external observer. This position must be erroneous, since there is always the possibility for the external observer to make use of interference properties between elements of the superposition. The reason he believed that all these branches existed was it's always in principle possible to an experiment to detect one of them. It's not because he had some kind of basic metaphysics about branches must correspond to worlds. It was, you can always do one of these interference experiments like W outside the box to show that there are two branches there. On Everett's understanding of the Wigner's friend story, the external observer may always in principle perform a measurement that would show that the system is in the superposition predicted by the linear dynamics. That's why you have to have both branches. So back to the problem at hand. Everett understood having a typicality measure not as giving probabilities, but it was a necessary precondition for talking sensibly about the statistical properties of typical branches. If he wants to talk about typical branches, he needs a notion of typicality. The main result of his thesis wasn't that some branches are more probable than others. They're all probability 1. The main result of his thesis was that almost all branches in measure m will exhibit the standard quantum statistics in the limit as the number of measurements one performs gets large. Now, not almost all in a counting measure, but in measure m. This was the single fact that he took to be most important in understanding pure wave mechanics. So this is how he did it, and I'll sketch this quickly. This is what he took to be the most important thing that he did in physics. He then retired from physics and went to work as a defense analyst in Washington, D.C. But before he did that, he did this. Consider a measuring device that's ready to make a series of measurements on each of an infinite series of systems Sk. So S1, S2, S3, and all the Sk are in this initial state. Suppose that M interacts with each system in turn and perfectly correlates its kth memory register with the x spin of system Sk by the linear dynamics. We don't allow any collapses. This is going to produce an increasingly complicated entangled superposition. After the first measurement, the measuring device will be in a superposition. It's just measured system 1. It'll be in a superposition of getting up for that measurement and getting down for that measurement with coefficients alpha and beta. After 2 measurements, it's measured system 1, then it measures system 2. The measuring device will be in a superposition of getting up for its first measurement, up for its second, up for both these systems, down for the first, up for the second, down for this, up for that, up for the second, down for the, up for the first, down for the second, down for both. And the coefficients then are products of the alphas and betas. After 3 measurements, we have a more complicated set. You can see the branching here. The first measurement gives us a superposition of the result up and the result down. The second measurement gives us a superposition of up, up, down, up, down, down, down. In the third measurement, we get every possible combination of ups and downs for the 3 measurement outcomes. And each one of these branches is now weighted by a complex valued amplitude. And the typicality measure that Everett has for these branches is the norm squared of that amplitude. So here's what he proves. And in fact, if you were my graduate student, I would have told him try again, because the proofs are kind of sloppy. He sketches this first theorem, and then the second one he just kind of waves his hands out. But the first theorem is a relative frequency theorem. You can read it at your leisure. The second theorem that he waves his hands at is a randomness theorem. And these have to do with limiting properties as M performs more and more experiments of the sort that we just described. Now, the upshot of these 2 theorems is the following. In the limit, as the number of measurements gets large, almost all branches in measure M will describe sequences of measurement records that are randomly distributed with the standard quantum statistics. This is what he wanted. Condensed down, and this is the key of his whole PhD thesis, the records of a typical relative observer, the records in a typical branch, the records in a typical world, will exhibit the standard quantum statistics, at least for this setup. It is, however, typically not the case that the records in most branches will exhibit the standard quantum statistics. That's something we discussed earlier briefly, but this fact came back to haunt Everett. 2 of Everett's strongest supporters were Bryce DeWitt and Neil Graham. Graham was one of DeWitt's students. They argued that Everett's typicality measure was unmotivated. As Graham put it, quote, "It is extremely difficult to see what significance such a measure can have when its implications are completely contradicted by a simple count of the worlds involved. Most worlds you don't get the standard quantum statistics in. So what's the explanation supposed to be here?" What DeWitt and Graham wanted was a theory where the simple proportion of worlds that exhibit the standard quantum statistics is large. Only then did they believe that one would have an adequate account of why one should expect one's experiments to exhibit the standard quantum statistics. Now notice, Everett wasn't explaining why we should expect. He was just saying in a typical world with this notion of typicality, they will exhibit the standard quantum statistics. So you might be getting the sense that DeWitt and Graham want a stronger explanatory theory than what Everett provided. As a result of this commitment, here's what Graham did. Graham stipulated a rule for how worlds split such that the number of worlds that exhibit a particular outcome after a measurement interaction is proportional to the square of the coefficient on the term describing that outcome. Now, some of you are right up to speed here. This is a very amusing thing to do. We have a technical term for this in philosophy. We call this blatantly ad hoc. So here's what he did. on Everett's view, there are two worlds, one where the friend gets up, one where the friend gets down, two branches. On Graham's view, there are a whole bunch of worlds. Alpha squared % of them, the friend gets up. Beta squared % of them, the friend gets down. So if I choose from among those worlds at random, I will get the appropriate quantum probabilities for the up and down result, because the quantum probabilities are alpha squared and beta squared for each of the outcomes. Okay. Now, Graham didn't take his proposal to be ad hoc, but there it is. This ad hoc splitting procedure ensures that almost all worlds by simple count will exhibit the standard quantum statistics. So Everett was still around. He was working in Washington, D.C. at the time, but he was interested in how other people responded to his work. And this is something that we didn't know about Everett until much later. He would go and photocopy when John Bell wrote something about him or when DeWitt wrote something about him. And he'd take these photocopies and he'd write in the margins of the photocopies. He also had the DeWitt-Graham anthology on the many worlds interpretation of quantum mechanics that came out in 1973. And Everett, in his personal copy, wrote in the margins of this anthology that contained his PhD thesis and papers responding to it. Both of the DeWitt and Graham papers were in this anthology, following after Everett's own paper. So we know what Everett thought about Graham and DeWitt because of the marginal notes that he wrote next to the complaints that they waged against him. Where DeWitt claimed that Everett's typicality argument was unsatisfying, Everett wrote in the margin, "only to you." Where Graham claimed that Everett's typicality measure was unmotivated, Everett wrote in the margin, "bullshit." This is how he spent his evenings when he'd come home from work. Everett was certainly free to use whatever measure of typicality he wanted to show that relative records in a typical branch will exhibit the standard quantum statistics. Further, we've seen that the measure he used was, it's natural enough, right? He imposed these constraints. They're reasonable enough constraints. They give him a measure. He uses it, and then he shows that in that measure of typicality, he gets the result he wants. That DeWitt and Graham believed that making something true of most branches by count was the only way to explain why an observer should expect his results to exhibit the standard quantum statistics, it actually tells us something more about their background commitments, what they wanted from a theory. To begin, they took this talk of worlds somehow inhabited by copies of the observer much more seriously than Everett himself did. Again, Everett didn't ever write about many worlds. He didn't describe the branches as worlds. He said there's a sense in which there's different results for the observer. There's a sense in which there are different observers afterwards. And to cash that out again would take some care and subtlety. DeWitt and Graham simply believed that there were many worlds inhabited by copies of the observer. Second, DeWitt and Graham seem to have wanted standard probabilistic predictions from the theory. Now, if my proposal here is right, Everett didn't want standard probabilistic predictions from the theory. He just wanted to show that a typical world exhibits the standard quantum statistics. And that's rather weaker, I suggest. Finally, it appears that DeWitt and Graham were guided by a familiar but confused intuition, I suggest. Their intuition was a principle of indifference. And this makes its appearance here because it turns out to be important for the history of no-collapse formulations of quantum mechanics from the 1970s until now. People will oftentimes, in their derivations of probability from pure wave mechanics, pull in a principle of indifference and put it to work. So what licenses you to pull in the principle of indifference? So in this case, if there are n possibilities, then in the absence of other information, one should assign probability 1 over n to each. Now you can see how this worked for DeWitt and Graham. Their picture was something like this. I perform an experiment. It generates a whole bunch of worlds. Most of those worlds have the standard quantum statistics, in fact, just the right proportion. And then I find myself in one of those worlds at random. What do we mean by at random? Well, with probability 1 over n in each. They also required a finite number of worlds, the way they described it. And then I have the standard quantum predictions because that's the probability of getting that result. So that's supposed to be the rough picture. You can see how the principle of indifference shows up here. It shows up in what's the likelihood of me finding myself in one of these worlds. Now, these are called self-location probabilities in modern language. But they're already up and running, at least in the background, for Graham and DeWitt in the early 1970s. So they're using a principle of indifference, it seems, for self-location probabilities. There are several problems with this. And let me review these quickly. Let's review them together quickly. First, and we know this because we're philosophers of science, a principle of indifference always depends upon a choice of partition. Since pure wave mechanics specifies no single canonical decomposition of the full state into branches, the theory does not tell us what set of branches one should use in assigning each branch probability 1 over n. One would have to choose a canonical decomposition of the state before one could even get started at applying a principle of indifference. Further, if one does the natural thing and chooses a determinate record basis for the decomposition, and then assigns branch probability 1 over n to each branch, one typically gets the wrong quantum probabilities. Graham's strategy of stipulating just the right number of duplicate worlds to get the right quantum probabilities is blatantly ad hoc. DeWitt and Graham do not deduce the standard quantum probabilities from pure wave mechanics. They put them in by hand. Even if we grant them the principle of indifference, they're just sticking the probabilities in there by how they partition. We can get whatever probabilities we want by playing around with the partition. And that's what Graham's doing when he stipulates these quantum mechanical worlds are being duplicated. One needs a principle of indifference to get probabilities at all on an approach like this. But, and this is a more general philosophical point, I think there's no reason to suppose that one can get indifference for free as a basic principle of reason. And there are a number of famous arguments. Let me just say a couple of things about this that are relevant here. The directive to assign probabilities 1 over n to each of n possibilities, it doesn't even mean anything without a choice of partition. In this particular context, there's no canonical choice of partition, but there's another problem. One would have to believe that there's always a canonical choice of partition in order to have a general principle of reason with any content here. And I take that to be a serious problem with getting a principle of indifference for free as a constraint on reason. Further, nothing goes wrong for a rational agent if she does not assume a principle of indifference. A good Bayesian might assign prior probabilities in any non-dogmatic way to her n hypotheses without fear of finding herself committed to a Dutch book or failing to respond appropriately to relevant evidence. You have to say something that goes wrong if you assign probabilities in a different way, and I don't see it. The upshot is that if one needs a principle of indifference to explain quantum probabilities, then you need to explicitly add it. I think you add it to your theory. That's the honest thing to do. I don't have anything against principles of indifference. It's just you don't get them for free. You specify a partition, you specify how the principle of indifference works, and you add it to your theory that's doing the explaining. But it would have been inappropriate for Everett to appeal to a principle of indifference, I think, inasmuch as he took pure wave mechanics to be quantum mechanics without probabilities. And the reason we need a principle of indifference is to get probabilities. That's the thing that if we add to pure wave mechanics says something now about probabilities, probability 1 over n. But if we don't need probabilities, we don't need a principle of indifference, and I don't think Everett did. He was concerned with describing properties of typical, not probable branches. And since he was clearly free to use any measure of typicality at hand, DeWitt and Graham's criticisms have little purchase, I think. It's just he was after a much weaker kind of explanation than what they wanted. Everett took the standard quantum statistics to be satisfactorily explained by the fact that they're characteristic of a relative observer's relative records in a typical branch. They're characteristic of the records in a typical world. If that's all I want from an explanation, he gives a pretty good one. Of course, he has to assume a notion of typicality to get it. This modest explanatory goal still requires auxiliary assumptions that go beyond pure wave mechanics, but they're much weaker than what one would need to get probabilities over branches. So let's recap briefly what Everett needed to add. He needed to add a distinction between absolute and relative states, which pure wave mechanics didn't have. That gives him a more subtle interpretation of the states. And then he needed to add a specific notion of typicality. Then under the conditions he specifies, he can show that typical branches exhibit the standard quantum statistics. If one insists on having probabilities out of the theory, one must add something that explains why one's record should be expected to be typical in the particular sense specified. The honest thing to do would be to add these further assumptions to one's full specification of the theory. So here are the methodological morals. This is a concrete case, and whether we're interested in pure wave mechanics or not, we should be, because it's a good starting point for resolving the quantum measurement problem, whatever other problems it might have. But there are things to reflect on concerning general philosophy of science here as well. So these are meant to have a dual edge to them. Pure wave mechanics says nothing whatsoever about probability. Indeed, by itself, it describes neither chance events nor uncertainties on which probabilities might supervene. Hence, if one wants the standard quantum probabilities, then one needs to supplement the theory with auxiliary assumptions that specify two things. One, what those probabilities are, and two, what the probabilities concern. And given the central explanatory role they play, such auxiliary assumptions should be included in one's specification of the revised theory, I think. And this is the normative thing. This is the normative methodological claim. If I'm claiming my theory explains probabilities, then it better be the theory that explains the probabilities and takes the weight of it. It is tempting to claim that one can deduce the standard quantum probabilities from pure wave mechanics alone. What makes this tempting is that it sounds like magic. It would be. But it's for precisely this reason that one has a special obligation of clearly specifying what else one is relying on to get probabilistic predictions. If one wants a formulation of quantum mechanics that predicts the standard probabilities, then one needs a theory that's significantly stronger than pure wave mechanics. That's the moral of the talk, the specific moral of the talk. This is the no magic constraint. Thanks.
Good, so we've got plenty of time for questions. Yep, Anton, go ahead.
So I think I'm still missing the sense in which what Everett was doing turns out to be less bad than what Graham and other people were doing.
Oh, I'm not sure it's less bad.
Okay, well,
Yeah.
please you can just enlighten me. Like, because there were points where it sounded like you said things like, look, Everett can specify typicality however he likes, and that the things he's appealing to here look relatively natural, and that seems to be a good thing.
I was trying to give him the benefit of the doubt. If you detected that what he was up to was a little suspicious, that's right too. He's not getting all that he gets from pure wave mechanics alone. He sneaks in this distinction between absolute and relative states. That's big. Why is that big? Well, because our experience for Everett is going to be explained by relative states, not absolute states. If he doesn't have that distinction, he doesn't have the thing in his theory that's going to explain our determinant experience. He also sneaks in this notion of typicality. Now, it's funny to see the genesis of this. What he said in the first draft of his dissertation is he said, we're going to see that this notion of typicality is not as arbitrary as it might at first appear. And then he goes on with his argument. In a later draft, he says, we're going to see that the only natural notion of typicality is the following. It's human nature.
I mean, as a takeaway, because it seemed like the takeaway might have been that the principal indifference thing going on to deliver probabilities was somehow worse off.
Well, it's a trade-off. And here's the trade-off. Everett only has to add these two relatively minor assumptions, a distinction between absolute and relative states. You might say major, but let's compare them a bit. A distinction between absolute and relative states, and then this notion of typicality. He doesn't get probabilities from that. That's the downside. He's assumed some extra stuff, and he didn't get probabilities, standard probabilities out of it. he just got the ability to say a typical world in this sense is going to exhibit the standard quantum statistics. Now, what Graham and DeWitt want, part of what they want is virtuous. They want a stronger explanation of our experience than that. They want to know why I should expect in the future to get the standard quantum statistics. They want to know why it's probable that when I perform my next X spin measurement, I get up if the coefficient is if the norm square root of the coefficient on the up term is much bigger. That's a stronger explanatory goal. They need stronger assumptions to get that goal. So it's not that they're doing something that's not virtuous. It's just that you get out what you put into the theory. There's no magic here. They're going to need a stronger assumption like a principle of indifference in order to connect up the typicality measure with probabilities. The good side of that is now they get probabilities.
If I was just saying, I guess what it seems like to me is that if Everett is going to do the explanatory thing that he was claiming to, which is something like explaining I think it was the appearance of the quantum mechanical statistics or something like that, by appealing to this typicality measure that he has just cooked up, that he's not in any better position for that explanatory project.
His explanation is so weak. Yeah, so if that's what you mean it's weak, I agree. If what you mean is he still had to assume stuff that went beyond pure wave mechanics, I agree with that too. So the thing to do, I think, is to reflect to ourselves, what do we want from our physical theory? One of the things that's attractive both to physicists and philosophers is to get something for nothing, to Americans. But that's what you can't get here. And so I don't care how strong our explanatory demands are. It's just that what we want to do is make sure that the explanatory resources of our theory are articulated in such a way as to satisfy those demands if we're claiming they do. And that's the general point, methodological point concerning clarity in explanation here.
I was wondering if you could say a bit more about what justifies that particular measure as one of typicality. I think this is connected to the question. So if what it is we can just specify any old function we want, okay, but then don't call it typicality, call it banana or whatever you want. If it's typicality, though, that carries with it, certainly in the English language, a lot of connotations. Right?
Yeah.
The typical things they tend to happen. Wait a
Yeah.
second, probably
Yeah.
So
I think I
feel like he's pulled a sort of semantic fast one on us.
You
Like,
bet.
that particular label.
There's no question at all that that's part of what's going on when you choose that label. Because, as you put it, in the English language, typicality is something that's closely connected to probability. Now, I've been leaving it here as an undefined notion, right? It's just a typicality measure. And this typicality measure satisfies the properties for a formal probability measure, right? It's the probability 1, and we go through what it does. But we're taking Everett at his word that it's not supposed to represent probabilities. And that's part of the game. The reason he's able to shift, the reason he's able to offer his explanation, see, if I told you a typical world is going to satisfy the standard quantum statistics, you might say, our world's typical, so we should expect it to satisfy. But we've slipped there. We've introduced a background assumption that ties typicality to probability. The thought, and this applies to quantum mechanics, I could list a dozen papers that claim to produce, to derive the standard quantum predictions from pure wave mechanics, right? And they work in different ways. But many of them run through typicality, I think, for precisely this reason. Because you can say anything you want about typicality because it doesn't really mean anything. But then it's easy to shift over to claims about probability. It happens here, and it happens in statistical mechanics all the time. I can introduce a typicality measure in statistical mechanics. Nobody's going to stop me from doing that. And then I'm going to let the reader assume that typical means probable. I never said it. But if they assume it, it might make my explanations look a lot stronger.
Do you think Everett has done that? Did that? Do you think he...
Well, he didn't choose the name for nothing, right?
Yeah.
Yeah. So, and this is part of the DeWitt-Graham complaint against him. his notion of typicality is entirely unmotivated because a typical world, right, if we count them up, does not exhibit the standard quantum statistics. Usually our notion of typicality really hooks on to counting. But if he just wants a measure with these properties, he gets it for free. He calls it a typicality measure. That's part of the trick.
So I think this is a very similar question, but sort of whether it's explanatory or not, I just want to check that I'm understanding. If I have sort of Everett's theory just with the typicality measure, does the theory make any predictions at all? I mean,
A typical world will exhibit the standard quantum statistics. For you to think that makes predictions, you might want to shift and think, our world is typical. We should expect our world. But the theory doesn't tell us to expect our world to be typical or anything like that. In fact, and this is the part of the talk that we just set aside, we're not really clear what it means, our world, phrases like that in the context of a theory like this. Something that you've seen 2 or 3 times during the talk, but I'll put it in different words. Because this observer outside the box can perform a measurement to detect both branches of the superposition, both worlds. Worlds on Everett's view are not causally closed. In what sense are they worlds then? If I can detect them, they're not causally closed. So there's a big thing that we haven't talked about, and that is how does his account of basic experience itself work? When there's supposed to be these 2 copies, but the worlds they're not really copies because, right, there's no violation of conservation of energy or mass. He says there's really just one world with different branches. How are we supposed to understand that? That's something we want to get clear on too if we want to put pressure on his statistical argument. I've talked a lot about that in the context of other papers. I wanted to move over to the probability problem and show part of the sleight of hand that takes place here. And I take a similar sleight of hand to occur in statistical mechanics too, when people take themselves to be deducing probabilities from a deterministic theory. In that case, it might be Newtonian mechanics, without introducing any probabilistic assumptions. I don't have any problem with this, as long as you make your probabilistic assumptions that you're really introducing explicit.
Would you then say that a perfectly good foundation for quantum mechanics is to take Schrödinger and to take Born? Because Born then had turned Schrödinger's way into a way of calculating probabilities, thereby saying, well, we should use probabilities, and here is a way to calculate them. In other words, why not treat Born and Schrödinger as equally worthy of the Nobel Prizes, which Schrödinger got early and Born after some time?
Well, they got their prizes. So the Born rule on the standard collapse formulation of quantum mechanics is that rule 4.2. But we could be more operationalists or instrumentalists about it and just take it to be an algorithm for tying the current wave function to probabilities. It's not entirely clear how to do that because we have to account for things like when I repeat my measurement, I'm guaranteed to get the same result. That's one of the things the collapse dynamics does for me, is when I make my measurement, I get this result with such and such probability. Now if I repeat it without dispersion, I'm guaranteed to get the same result. So we'd need to be careful about how we proceeded, but there may be an operational view that goes just like that.
I would say that's what I've done. Right? I mean, I choose histories, assign probabilities. It requires a generalization of Born's rule, but the genius said use probabilities, and so I am suggesting we should adopt as fundamental axioms a probability along with Schrödinger.
I take your view to be very much an operationalist view. One of the things that we give up on a path like that is something that these guys all seem to have wanted, and that is a single matter of fact at all times.
So this is kind of a follow-up on Allison's question as well, and it has to do with Everett's motivations for using the coefficients in his typicality measure, right? So one thing you could say there, which seems plausible to me, is he's importing what he knows from Rule 2 about what the coefficients mean, right? That is, they're related to these probabilities. You said that, as I recall, correct me if I'm wrong, the reasons that he had were, well, one, they're numbers that they're in there, so you might as well use them.
Yeah.
And
I like that as a summary of one. That's exactly the idea.
You know, then why are they there? What do they mean, right? And the second thing he said was somehow that they're tied to what we can determine empirically, right? But
well, he wants it to be a function just of. He wants to exclude phase information because we can't determine the phase information.
Which you do by squaring.
That's right. Yeah. Look, he knows what he wants. He can't forget it. Everett learned the standard collapse formulation of quantum mechanics that I threw up there. That's the theory he learned. It was translated into English from German when just before Everett went to Princeton, at Princeton. Right, so this is the formulation of the theory everybody was looking at. He knows what's going to work there. Is he back engineering it? Is he reverse engineering in order to get the results he wants? Even if he said he wasn't, I'm not sure we could believe him, given human nature as we find it.
Thanks. I was wondering the extent to which your problem hits any scientific theory which includes probabilities, because in any such theory we would have some possibility of there being a very improbable line of events, and we would have to invoke some assumption that we're in a sort of likely sequence rather than an unlikely sequence, and then it seems like if we need to include that assumption in any probability theory at all, then it looks like we've got some circularity then again in our explanation.
Well, I'm not worried about probabilistic assumptions. It's just that what I think methodologically is we stick them in the theory. The standard collapse formulation of quantum mechanics, I'm not arguing in favor of it, but one virtue it has is it's explicit about where probabilities come from. There are two processes. One's deterministic and one's stochastic. The stochastic process has these probabilities associated with it. Now, the theory is, on a strict reading, logically inconsistent. That's a problem. On a charitable reading, it's incomplete because it doesn't tell us what constitutes a measurement. Right? On a strict reading, where I suppose that measuring devices are physical systems like any other, we get an inconsistency. So I'm not arguing for the standard collapse formulation of quantum mechanics, but there are formulations of quantum mechanics like GRW and Bohmian mechanics that make perfectly good and explicit specifications of where the probabilities come from. Now, some Bohmians want to then show that's the only probability measure. They say it's the only equivariant probability measure, so it's canonical, and they want to make the assumption that involves probability in their theory seem really natural. People are embarrassed about probabilities. Don't be embarrassed. If you need them, stick them in your theory. Show what's doing the work.
If I say this, everybody will rightly think here's this naive, total naive outsider, which is correct.
I won't.
But here goes. So, one way of looking at both the indeterminacy that you lay bare in criticize in saying that the typicality measure looks arbitrary, and also as a second point, the freeness you're laying bare of how Everett thought about these things not as complete and causally closed worlds. Both of those strike me as places where maybe we don't know what to do because we need new physics. is not a possibility that's, well, sorry, I take it. In your physics, I mean, so maybe these splittings are what's generating dark matter, right? You get all these.
Well, that would
all
be
these
that would
interactions.
require new physics, right? That
I know, but
Yeah.
I'm saying these seem to be spots in our established story
uh-huh.
that we're trying to fill with merely conceptual ideas. But if we're ready to acknowledge their gaps, then shouldn't we be looking to fill them with new physics?
I think so. That's what's at stake here, and there's a methodological moral to this as well, at least from my perspective. When we work on something like the quantum measurement problem, it's not hands off. We're messing around with physical theories, how they're interpreted and how they're formulated. What's at stake here in dropping the collapse dynamics is changing the dynamics of the received view of quantum mechanics. That's as physical a proposal as somebody can have. And in Bohmian mechanics, what's involved in introducing the new dynamics is introducing a new physical dynamics. In GRW, you introduce a new physical dynamics. We're actually in the trenches here, constructing new physical theories. And what right do we have to do that? Well, because the old ones are really bad. Everybody lends a hand, and we see how far we can get with the new physics. That said, none of these have the ring of truth to me. And so oftentimes I find my job, the job that I can honestly pursue, as pointing out what you've called these gaps. I take these to be kind of explanatory gaps in the theories, places where we would think that we have every right to have a clear explanation, but we're not getting it. Now, a number of people have proposed that maybe quantum mechanics is just the kind of thing that you're not going to be able to satisfy standard explanatory demands in this context. If that's right, that's big news, right? Because it means we misunderstood how science works a little bit. Because we're imposing constraints on these, explanatory constraints on these theories that they can't satisfy. That would be interesting. I'm going to aim to get the richest explanations I can from these theories until I run out of strength to do so. And then in my old age, I'll be one of the people saying, maybe we can't do any better than this. But I like to think I'm going to be saying, yeah, it's for the next generation to sort this out. I've done my best.
Thanks a lot, Jeff. I don't want to drag you too far into things that you've talked about elsewhere, but since you said a little bit about it in the Q&A, and since you alluded to the fact that what so many people describe as the Everett interpretation is really not quite what he has in mind.
It doesn't seem to be what he had in mind.
Could you say just a little bit more about what it means for him to say that individual branches are like
worlds?
How do you put it?
Perfectly respectable world. That's what he said. That's what he said to Shimoni.
Part of that is what is perfect respectability
Mhm.
in this context, and then what is like, because that suggests that in some respects.
This is ask just like a philosophy question. Yeah, so we have a bunch of new information about Everett. How this happened is that Peter Byrne was interviewing Everett's son, Mark Everett, who's the lead singer for the Eels, right. And lives in Silver Lake. And what happened is that Peter, I'd never met Peter, but he called me on the phone and said, I've been interviewing Mark Everett for this story for Scientific American celebrating the 50th anniversary of pure wave mechanics. And you're not going to believe what I found. I found in his basement he has these boxes of Everett's notes. Can you come help me sort through these? And so I got involved in it, and we went and we started sorting through these boxes. And I learned a lot about Everett's view on things. I didn't learn very much about worlds because, again, even in his notes, he doesn't talk about worlds. I can only think of 3 times that he mentions worlds at all. One was in a letter towards the end of his life. There's the Shimoni quote, and then there's one other. So we have a bunch more information than we used to have, but I can't really explicate what Everett meant by respectable world. But I can tell you what he meant by empirical adequacy of his theory. And that should be responsive. So Everett had a view on empirical adequacy that I think is closest for people who have done their philosophy of science homework. It's closest to von Frausten's constructive empiricism. It's kind of half-baked because Everett was a graduate student in physics working on this stuff, but here's how it worked. Everett took a physical theory to be empirically faithful. That's his term. If one can find one's experience appropriately in the model of the theory. So you construct your model of the theory, and then you have your experience, then you go over to the model and you try to look for your experience somewhere. We saw how you can find it. You give me any set of results that you got for your experiments, I'll go and find them in the theory. I'm going to find them in one of the branches. That finding is what he took to the theory being empirically faithful over the actual experimental results that I get in the laboratory. His metaphysical commitments were very weak. He took himself to be an operationalist, and he liked the logical positivists that went earlier. He actually had correspondence with logical positivists and said his view was very similar to the views that they held. So one thing that he certainly wouldn't say is start pounding his fist down on the table and saying, these are worlds, gosh darn it. The reason he believed that these branches were all real, equally actual, is the operationalist reason. If I were to perform this external measurement, I would get +1 for the A observable because the state is this superposition. But again, this is a very weak kind of explanation for the results of our measurements. It's not that the theory predicts them. It's that you give me your results, I can find them in the theory. And when I find them in the theory, I find them associated with the typicality. And you saw the rest.
That's interesting because if you have that weaker conception of how to interpret the theory, then you have a corresponding conception of what perfectly respectable is.
In this sense.
Anything that satisfies that weak conception.
Yeah. So this.
Branches aren't like that world. They just satisfy the. They're not like worlds per se. I mean, there's no relation between branches and. There's no metaphysical claim being made at all.
No metaphysical claim, yeah. I saw that's what you were getting at. There's a representational claim. The branches represent the experimental results I got in the laboratory.
Thanks a lot. I just wanted to ask if there are any examples, maybe in statistical mechanics, maybe elsewhere, when you get this measure, typicality measure, that deviates from what you would expect from just counting the states and taking a proportion of the raw number.
Well, in some situations, yeah, so that's a good question. So the question is, how often does it happen that the typicality measure you have in mind is biased? It's not the 1/n fair measure. It happens quite a bit. It happens in Bohmian mechanics. The measure one needs there is something called the equivariant measure. It happens with Gibbs measure in thermodynamics. But oftentimes, Lebesgue measure works well as your measure of typicality. In that case, that's the unbiased equivalent for a continuous set of possibilities. So sometimes it works, sometimes it doesn't. The most recent paper I know that's been written on deducing quantum probability, the standard quantum probabilities from pure wave mechanics, actually introduces a new idea of what it means, a new principle of indifference. And this new principle of indifference doesn't assign equal probabilities. It assigns exactly the quantum probabilities. I'm glad some people got that.
I just sounded in the Q&A at least that people were worrying that this measure is in its own way, Everett's typicality measure is in its own way on most space, ad hoc and on most spaces, reverse engineering. So I'm wondering what kinds of motivations would like to see.
Yeah. Yeah, I think it might come back to how we use the term typical in the English language. I typically, and I'm referring to by count, I typically use the word typical to refer to counts.
But experience is not an unbiased, uniform sampling from all possible states.
No, that's right. And but this is the methodological thing we started with. It's part of our job to look at arguments and try to tease out the implicit assumptions and make them explicit and better understand what's going on. That's not an easy part of the job. And part of it is that it's so easy to smuggle things in sometimes because of little linguistic tricks, like the special semantic relationship between the word typical and the word probable, the word typical and the word expected.
Thanks. That was great. That was really informative.
Thanks, John.
Statement and then a question. I just take it as a rule of thumb that if the theory of fundamental particles has to make non-trivial assumptions about human consciousness, then it's really indeed probable.
I couldn't agree more. That sounds like desperation to me.
So now let me continue. I'm just trying to wrap my head around how the typicality assumption is supposed to work. And I think it goes like this, but tell me if I'm getting it wrong. So I'm an experimenter. I'm about to do an experiment. There are many, many branches. Right? I do the experiment. Now there's a copy of me, or there are many versions of me that experience every possible outcome.
So what's the probability of you experiencing a particular outcome? 1.
It's definitely going to happen. I expect that
That's
there's
right.
a me experiencing every possible
Yeah.
outcome.
Good.
So what's the typicality doing? The typicality seems to be saying that my consciousness is preferentially going to be realized in certain of the branches. Is that it? Because boy, that's you know.
I'm so glad you said this and I didn't. Good. So that's what I meant towards the end when I said if we want to introduce probabilities here, we need to do 2 things. We need to introduce the probabilities, and then we have to say what they obtain for. On the description you just gave, it's a self-location probability, the probability of finding myself, my conscious self, in one of those branches, something like that. This is exactly how Everett, or how Albert and Lower's single mind and many minds formulations of quantum mechanics work. They have self-location probabilities. The self-location probability is the probability of my mind becoming associated with one of these future copies. And those probabilities are given by rule 4.2.
But does that mean that all the other copies of me don't have minds?
Yes. I'm answering this post-theoretically, right? I'm just telling you how it works on the Albert Lower. They call these mindless hulks.
So this really is a theory of consciousness?
It's really a theory where there's a strong mind-body dualism. How strong? Well, the mental state doesn't supervene on the physical state here. That's how strong. Yeah. And that's how it works. And they took their many minds and single minds formulations of quantum mechanics to be versions of Everett's formulation of quantum mechanics. Now, nowadays, and this is for the people who come in contact with this, you can't avoid hearing about Everett. And oftentimes when Everettians talk about Everett, their probabilities they talk about are self-location probabilities. I know exactly what self-location probabilities mean in the Albert Lower theory. And they rest on this special crazy metaphysics. I often don't know what my colleagues are talking about when they talk about self-location probabilities. We really need to know what that self-location event is, or relation is, or something like that, to know if it's the kind of thing that a probability might supervene on appropriately.
So I can't resist. We're dealing with a zombie theory where
Yeah,
virtually every living person is a zombie.
that's right. And in fact, Albert and Lower have this argument in their original paper where this is why they moved from a single mind theory to a many mind theory. So on their first theory, every observer has one mind, and that mind then gets associated with one of the branches. The problem is if those associations are independent of each other, your mind might get associated with the spin-up branch, and mine might get associated with the spin-down branch. And so when I'm talking to, to you, and I say, what did you get? What I'll hear, and this is a long story, it follows from something called the suggestive properties of the Barrett theory. What I'll hear you say is something that agrees with what I actually got. But there won't be anyone I'm talking to. I'll be talking to a mindless Hulk. When you talk to me, there won't be anyone you're talking to. You'll be talking to a mindless Hulk. And so to solve that mindless Hulk problem, that's why they went from a single mind theory to a many minds theory. So in a many minds theory, you have a continuous infinity of minds associated with you, and I have a continuous infinity of minds associated with me. They all associate independently, according to the quantum probabilities. So about half your minds go down this path, and about half go down this path if the probabilities are equal. And about half mine go down this. What that guarantees is I'm always talking to someone. That's how serious Albert and Laura took this. And I remember I was at Columbia, I'm in the hallway, and Albert just got, for his book, Quantum Mechanics and Experience, he got a copy of the review from, I think it was one of the London papers. And the reviewer said, Albert's finally done it. He solved the quantum measurement problem with the many minds formulation of quantum mechanics. This wasn't meant to be taken too seriously. It was meant as a clear proposal for what it would be to have self-location probabilities in the context of a theory like this. And it's remarkable that it requires this kind of strong mind-body dualism, and that certainly speaks against it. So those are the kinds of, when I said there are a number of ways to address the quantum measurement problem, none of them have the ring of truth to me. I'm trying to give you a sense of what it sounds like not to have the ring of truth. Job's done.
One or two more questions? Yeah, go ahead.
Just on this point, I mean, I would have thought that the self-locating probabilities have got to be subjective probabilities. I mean, in the many minds theory, there might be some kind of like objective.
So they're objective. Yeah. So, but if we don't want to, do something fancy with the metaphysics, then they're going to have to be subjective probabilities. But it's going to be tricky, right? Because my subjective probability, if I believe the theory, my subjective probability of getting spin up is 1. My subjective probability of getting spin down is 1. But you want to say, wait a second, what's the probability you are that guy? Well, this is what philosophers are good at, is thinking about situations like that. If the transporter on the Enterprise is broken, and I step onto the transporter, and it copies me into one copy that has a 1 on my T-shirt and a copy that has a 2 on my T-shirt, what's the probability I'm the guy with the copy with the 2 on my T-shirt? I don't think I have enough information to answer that question because I don't have an account of personal identity across time. Even for subjective degrees of belief, I would have to have an account of personal identity transtemporal, diachronic, in order for me to sensibly ask the question, I think, what's the probability I'm the guy who got up?
Immediately post-split.
Yeah.
You can have those kinds of things.
Yeah. So people are working on that. We'll see what happens.
And before we conclude, as we always do, it's not very appropriate today, but you were getting a nice overlap to the center. And now we can thank our speaker.
Thank you very much.